If you were to crack open your smartphone to move, I wouldn't recommend, unless you have a steady hand and a replacement ready, you wouldn't see any gears turning. There are no tiny pistons pumping, no miniature steam engines hissing. Instead, you would find a sleek dark slate of material nestled among colorful ribbons of copper and plastic. This is the microchip, the hidden brain of the modern world. It is the silent heartbeat of your car's engine, the watchful eye of the satellites orbiting thousands of miles above your head, and the tireless clerk managing the trillions of dollars that zip across the globe every second. The mystery of the microchip lies in its scale. We are used to thinking of power in terms of size, the thundering engine of a jet, or the massive turbines of a dam. But in the world of silicon, power is inverse to scale. The smaller a chip becomes, the more thinking it can do. It is a paradox that has defined the last 70 years of human progress. We have taken the raw material of the Earth's silicon, the very stuff of beach sand, and through a process that looks more like sorcery than manufacturing, we have taught it how to remember, how to calculate, and how to decide. As we pull back the curtain on this mystery, we begin to see that the microchip is not just a component, it is a manifestation of human willpower. It represents our desire to shrink the infinite complexity of the universe into something we can hold in our hands. It is the primary engine of the digital age, an era where the most valuable resource is no longer oil or gold, but the ability to process information at the speed of light. To describe a microchip simply as a circuit is like describing the city of New York as a collection of bricks. At its core, a microchip is an integrated circuit, a vast, sprawling landscape of electronic components etched onto a single piece of semiconductor material. If you could shrink yourself down to the size of an atom and walk across the surface of a modern processor, you would see a vista more complex than any urban skyline. You would see millions or even billions of transistors, each acting as a microscopic gatekeeper of electricity. The transistor is the fundamental building block of this world. Imagine a simple light switch. When it's up, the light is on. When it's down, the light is off. Now, imagine a switch so small that you could fit millions of them on the head of a pin. These transistors are the neurons of the chip. They don't just sit there. They work in concert to guide the flow of electrical signals. By turning on and off in specific sequences, they allow the chip to receive raw data, manipulate it according to a set of rules, and produce a result. The miracle of the microchip is integration. In the early days of electronics, if you wanted 1,000 switches, you had to wire 1,000 individual components together. It was bulky, hot, and prone to failure. The microchip changed everything by taking all those components, transistors, resistors, capacitors, and printing them onto a single solid piece of silicon. This transformed electronics from a craft of assembly into a science of architecture. We no longer build circuits, we grow them. To understand the internal life of a chip, we must understand its language, binary. While we use 10 digits to count and 26 letters to write, the microchip is much more Spartan. It speaks only in two states, on and off, 1 and 0, high voltage and low voltage. It sounds incredibly limited, yet this binary simplicity is the foundation of all digital complexity. When you tap an icon on your phone, a cascade of electrical signals is unleashed. These signals travel through the etched pathways of the chip, hitting those billions of transistors. Depending on the state of the transistors, the signal is either allowed to pass or is blocked. This is logic in its purest form. Through logic gates, arrangements of transistors that perform operations like AND OR, and not the chip can compare numbers, add them, and make if this then that decisions. A microchip is not a monolithic block of logic. It is a highly organized society with specific roles. Within a single chip, there are distinct neighborhoods, dedicated to different tasks. There is the arithmetic logic unit, ALU, the math whiz that handles all the calculations. There's the control unit, the manager that interprets instructions and tells the rest of the chip what to do. Then there are the caches and registers, tiny, ultra-fast memory banks that store the data the chip needs at this very microsecond. Crucially, all of this activity is governed by an internal clock. This isn't a clock that tells the time of day, but a metronome that sets the pace of the chip's operations. Every time the clock ticks, billions of transistors switch states simultaneously. This is what we mean by clock speed. When you see a processor rated at 3.5 GHz, it means the internal clock is ticking 3.5 billion times every second. This synchronization is vital. Without the clock, the electrical signals would collide and overlap, creating digital chaos. The clock ensures that every calculation is finished before the next one begins. It allows the chip to follow machine-level instructions, the granular, step-by-step commands that break down a complex task like open Instagram into millions of tiny, manageable mathematical operations. This occurs so fast that to us, the humans watching the screen, the action appears instantaneous. We don't see the billions of steps. We only see the result. The history of the microchip is a story of radical downsizing. In the 1940s, the state-of-the-art in computing was represented by machines like the ENIAC. This computer occupied an entire room, weighed 30 tons, and used 18,000 vacuum tubes. These tubes were essentially light bulbs that acted as switches, but they were fragile, consumed enormous amounts of power, and generated so much heat that they constantly burned out. The turning point came in 1947 at Bell Labs, where John Bardeen, Walter Brattain, and William Shockley invented the transistor. It was a solid-state device, meaning it didn't need a vacuum or a heated filament to work. It was smaller, faster, and much more reliable. However, the early computers built with transistors were still a mess of tangled wires. Each component had to be soldered by hand, a process that was expensive and prone to error. The eureka moment arrived in 1958, courtesy of Jack Kilby at Texas Instruments and independently, Robert Noyce at Fairchild Semiconductor. Kilby's breakthrough was the realization that all the components of a circuit, not just the transistors, could be made from the same semiconductor material. He created the first integrated circuit, IC, on a sliver of germanium. It was ugly with wires poking out of it, but it worked. This sparked a revolution captured by Gordon Moore, the co-founder of Intel, in what we now call Moore's Law. He observed that the number of transistors on a microchip would double approximately every 2 years, while the cost would decrease. For over 5 decades, this observation has held true, driving the transition from calculators that could barely add to smartphones that have more computing power than all of NASA did in 1969. If the microchip is a miracle of design, it is also a miracle of manufacturing. The process begins with common sand, specifically silica. This sand is melted and refined until it is 99.999999999% pure silicon, a level of purity that is almost impossible to find in nature. This silicon is grown into a large cylindrical crystal called an ingot, which is then sliced into paper-thin discs known as wafers. The actual printing of the chip's features is a process called photolithography. Because the circuits are too small to be drawn by any physical tool, we use light. The wafer is coated with a light-sensitive chemical called a photoresist. Then, a machine called a stepper shines high-intensity ultraviolet light through a mask, essentially a stencil of the chip's design onto the wafer. The light carves the pattern into the chemical layer. This process is repeated dozens of times, layer upon layer, using different chemicals and materials to build up the three-dimensional structure of the transistors and the copper wires that connect them. Today's most advanced chips have features measured in nanometers. To put that in perspective, a human hair is about 80,000 to 100,000 nanometers wide. We are etching structures that are only a few dozen atoms across. This level of precision requires an environment of extreme cleanliness. A modern semiconductor fabrication plant, or fab, is one of the cleanest places on Earth. A single speck of dust thousands of times larger than the features on the chip would be like dropping a boulder onto a city. Workers must wear bunny suits to prevent their own skin cells or hair from contaminating the air, and the air itself is filtered hundreds of times an hour. It is a process that combines the most advanced chemistry, physics, and engineering in human history. Not all chips are created equal. Just as a city has different workers for different tasks, the digital world uses specialized chips to handle different types of data. The most famous is the Central Processing Unit, CPU. This is the generalist, the jack of all trades. It is designed to handle a wide variety of tasks, switching rapidly between running an operating system, handling user input, and managing background processes. If the chip is a brain, the CPU is the frontal cortex, the part that handles logic and reasoning. Then there is the graphics processing unit, GPU. While a CPU is like a high-performance sports car, fast and agile, a GPU is like a massive fleet of trucks. It is designed for parallel processing, doing thousands of simple calculations all at once. This is essential for rendering the millions of pixels on a screen, or for the complex math required for modern artificial intelligence. In recent years, we have seen the rise of even more specialized chips. Neural processing units, NPUs, are designed specifically to mimic the way human brains learn, making them incredibly efficient at tasks like facial recognition or voice translation. Application-specific integrated circuits, ASICs, are chips designed for one, and only one purpose, such as mining cryptocurrency or managing the sensors in a medical device. Despite their different architectures, they all share the same DNA, the hyperfast switching of transistors on a silicon substrate. It is easy to think of microchips as something that belongs inside computers, but they have migrated into almost every corner of our physical reality. We are living in a smart world, which is really just a world where everything has a silicon brain. When you step on the brakes of a modern car, a microchip analyzes the speed of each wheel hundreds of times a second to prevent them from locking up. When you fly across an ocean, hundreds of chips in the cockpit and the engines are communicating with satellites to ensure you stay on course. In our hospitals, chips manage the delivery of life-saving medicine through infusion pumps and monitor the rhythms of the human heart through pacemakers. Microchips are also the guardians of our infrastructure. They manage the flow of electricity across the power grid, the distribution of water through city pipes, and the timing of traffic lights. They are in our refrigerators, telling us when the milk is low, and in our thermostats, learning our favorite temperature. They have become the silent sentinels of our civilization, working tirelessly in the background to make our lives safer, more efficient, and more connected. As we step back and look at the sheer scale of the microchip's influence, we realize that it has become the invisible framework of modern society. It has fundamentally changed how we communicate, how we work, how we travel, and how we entertain ourselves. Before the microchip, information was heavy. It lived in books, in filing cabinets, and in the physical presence of people. Today, information is weightless. It moves at 186,000 miles per second, carried on the backs of electrons flowing through silicon gates. But the impact of the microchip is more than just technological. It is philosophical. For the first time, we have created a tool that can think on its own, albeit in a very literal, mathematical way. It has forced us to redefine what it means to be intelligent and what it means to be human. As we delegate more of our memory and our decision-making to these tiny silicon slivers, we are entering into a new kind of partnership with our tools. The microchip is a testament to the fact that the most profound stories are often the ones we cannot see. We see the glowing screen of the phone, but we don't see the billions of transistors firing in perfect unison beneath the glass. We see the autonomous car driving down the street, but we don't see the millions of lines of code being processed in real time by a specialized AI chip. The microchip is the ghost in the machine, the silent force that turns raw energy into the digital experiences that define our lives. Our journey through the world of the microchip brings us back to where we started, with the realization that the mundane objects around us are actually containers for the extraordinary. The next time you pick up your phone or start your car, take a moment to appreciate the brain inside. Think of the purified sand, the ultraviolet light, the billions of transistors, and the generations of scientists and engineers who work to shrink a room-sized computer into something that fits in your pocket. The story of the microchip is not over. In many ways, it is just beginning. As we push toward the limits of physics, exploring new materials like graphene and new concepts like quantum computing, the brain of our machines will only continue to evolve. Thank you for joining me on this exploration of the invisible giant. I hope this look into the heart of modern technology has sparked your curiosity and given you a new perspective on the digital world. If there are other hidden stories inside everyday objects that you'd like to uncover, I'd love to hear your suggestions.